Okay, so this is the last concept we'll talk about today, which is weightlessness. And this is probably my second least favorite word in physics after deceleration, because everyone uses it wrong. I'll show you why. Well, there's two reasons. First of all, you understand now that there's a difference between weight and mass, right? Weight is a force, which is measured in newtons. It's a force by gravity on Earth. Mass is measured in kilograms. It's a measure of inertia. It's how much stuff in some sense, how much stuff there is, and the stuff basically resists motion. We don't know how that works, but it is, that's what mass is, right? That's how we define it. And everyone, if you go to grocery stores, you pick up an apple, you will ask how much this weigh, and then they'll tell you how much kilograms there is, or how much in pounds or kilograms. Kilograms and pounds is a measure of mass. That you should be asking what is the mass of this apple, not what's the weight of this apple. So, and if you talk about weight, everyone should be talking, they should be giving you in terms of newtons, but in everyday life, we never do that. And we basically cause all these physics students to get confused. Remember, you've learned the subject, so you accept that with everyday life, but you understand it's a misuse of this language. But that's a small issue. That's fine. And a bigger issue is when we talk about weightlessness. Okay, so usually you hear that in two contexts. One, you hear an astronaut, right, floating in space, right? That you hear it in this context, they feel weightless. First of all, they don't. We'll see why. A second context is if you go on a roller coaster, right? So you crest a mountain, and on the way down, right, you're sitting here and you feel very floaty, right? And this is another context where people talk about you feel weightless. Again, you don't. In both cases, you do not feel weightless. What is the more correct word is the lack of normal force, or normal forcelessness. Now, I'll be first to admit that will never catch on, and for good reasons. I don't want to keep saying normal forcelessness, but that is more accurate. And again, it's one of those things. Now that we'll talk about why, and once you understand why, you just accept the fact that everyone say, "Oh, this is weightless," but what they really mean is the normal force is zero, not the weight is zero. Now, that's very easy to explain. I'll explain an astronaut in the second case. This is very easy to explain. Well, what's your weight? Let's draw a free body diagram. The free body diagram. Let's make it a little bit more extreme, right? So let's go on a free fall Tower of Terror kind of a drop tower kind of thing, right? You have an elevator shaft and you're here, and let's say the elevator is accelerating so fast that your bottom leaves the chair that you're sitting on, and basically you have no contact force, right? So do you feel weightless? Well, it's just the same thing as the roller coaster going over a hill, right? That momentarily you're reducing basically your normal force. Why? Well, what is the free body diagram? You have a weight, well, that's always there. And if your butt is leaving the chair, then nothing is in contact with you, right? Then you have no normal force. So what's your weight? Your weight is still mg. Why? Does G change from falling over here? No, G is always 9.81, right? What's your mass? Well, hopefully you didn't lose mass you didn't lose an arm or lose a limb when you fall, right? So these two are still constant. Your weight is exactly the same anywhere from whether the elevator is still or not. What is different is, excuse me, is this. If you're sitting on a chair, right? If you're sitting on a chair, let me draw the free body diagram of yourself. Well, you have the weight, but then you also have a contact with your bottom, and there will give you a normal force. What do you feel? Do you actually feel the weight, or do you feel the normal force? You're sitting in your chair right now. What do you feel? Do you feel the force of gravity, or do you feel the force of the chair pushing on you? You feel the force of the chair pushing on you. In fact, this is so important. You never feel the force of gravity. We were talking about gravity for a long time. We talked about weight for a long time. You never feel the weight. What you do feel is the normal force. Something you should pause and slow down and really absorb that statement, right? What you really feel, if you really think about what you feel right now, what are you experiencing? You're experiencing if you're standing like me, the only thing I'm experiencing if I stand straight, right, is the force from the floor. My feet is experiencing a force. Your butt is experiencing a force if you're sitting down right now, right? You don't experience the earth dragging you down. Now, that is why over here, your normal force, if it's 0, then you feel, this is what we consider weightless. But now you understand this is better called normal forcelessness, right? It's exactly the same scenario over here. If you ask what's the force, you might ask what's the weight or what's the force on gravity on the astronaut. The force on it, well, I know how to calculate this, right? So this is R, right? It's pretty large, but it's not that large that makes it tiny. And G is a constant. M is the mass of the source. The other M is the mass of the test object, which is the astronaut and the Earth, right? All these stays constant. This does not. Hopefully, your mass does not disappear, right? And the Earth mass certainly doesn't change. This is a universal constant throughout the solar system. It doesn't change. And R is just the distance over here, right? It's a large number, so this is semi-small. But again, that's not the reason why you feel weightless. This is non-zero. The reason is because nothing else is pushing on you. Okay. Now you might say, hey, there is a spaceship, right? So I might let's draw the spaceship as well. Right, let's turn off the engine. So you're standing there, right? So you might go, hey, in that case, I will have a normal force. Why do I still feel weightless? So there's a weight or the force of gravity. Let's not distinguish them. But however, actually not, because you are in free fall. Your motion is going around here. So what is your acceleration? Your acceleration is going downwards. That's the centripetal acceleration you are in. If you turn off, that's why I turned off the engine, because if you're turning on the engine, then you will have an acceleration forward and you will experience a normal force from the back. But that's a separate thing, right? If you turn off the engine, both you and the spaceship is following this path. And both your acceleration, the acceleration of the astronaut, is the centripetal acceleration, which is from the reduced gravity over there, right? And the acceleration of the spaceship is also the centripetal acceleration that makes you go around in a circle. So when these two are the same, there's no extra acceleration. Here, it's basically the same. That's why it's the same physics. But this is what people mean with when they say it's the same physics as the elevator example, is because the elevator is accelerating downwards at G, and you are accelerating downwards at G. There's no difference. Over here, you are accelerating downwards at G, but the chair is not. So it's pushing against you. So you feel a normal force. But when both of them are accelerating down, so you don't feel any normal force, then this is the case where you do feel weightless. So astronauts, every single day, they feel exactly the same way as you go over the elevator or in a drop tower for that moment. You feel that for a small moment of time, they'll feel that throughout their orbit over here, because both frames, right, the frame and you are accelerating in the same way. Okay, so let's quickly also analyze the elevator case a little bit more rigorously if I draw this case, right? And just to emphasize why whenever you measure yourself, I'll explain the idea of apparent weight. Okay. So the idea is if you stand on a scale like this, and if the elevator drops, right, or start to accelerate downwards, you will feel a little bit lighter. And it has nothing to do with your weight. It's an apparent weight. And what you're really measuring is, you're not measuring your weight, you're measuring the normal force, right? So the biggest takeaway of this video is, every time you measure your weight, you're measuring the normal force. It's not the weight, okay? again, something that everyone is confused about usually. So let's start with if A is 0, right? What's the free body diagram? You have a weight and you have a normal force. What's the normal force? That's the force on you by the scale. Okay. Which one do you think the scale is measuring? A lot of people think the scale is measuring the weight. That's not true. Okay. I'll show you why, right? So if A is 0, so you have MA equals to F net. So let's put U, right? So if the whole thing is static, so this is 0, right? So you have 0 equals to N. So let's pick upwards as positive. Right? Then you have N minus W, all right? So that's fine. That looks good, all right? So W equals to N. That's exactly what we expect. And if now, if the elevator is now moving downwards, okay, so should I pick, let's see which way should I pick? G is the axis. Yeah, I'll keep it up. You know what? I'm gonna keep it, I'm gonna make it down. So I just have a little bit less negative signs. So I'm going to make that positive just to be consistent. Let's do this. Let's make this positive. So I will have W minus N, but I have exactly the same conclusion over here. All right. So in this case, right, it seems like the same situation, but you will have an acceleration that is non-zero. So what's the net force on you? The net force on you is also W minus N, right? And this time, let's say you're accelerating, so everything here is downwards, right? So this is positive, this is negative, because I'm making this downwards as positive. So you're accelerating downwards, the weight is pointing downwards, the normal force is pointing upwards. It's negative of downwards, right? So if you think that you're measuring your weight, then you have MA plus N, okay? But it doesn't change the fact that it's mg, right? You know weight is always mg. So the weight does not change. However, what you really are measuring is the normal force. Okay, I'll put that as the subject, right? The thing that you want to calculate, put that on the left, isolate that. So you have W minus MA, right? So that's mg minus MA, right? So mg minus MA, what is that? Well, that would be less than mg, which is your original weight, right? There is no original, your weight never changed. So what is less is the normal force is less. Here, if you see, right? In the case where acceleration is 0, so that's why I just want to make it consistent. They're both pointing downwards. So if the acceleration is 0, the normal force is mg. What is the normal force? That's the normal force on you by the scale. It's a little bit weird that you are measuring something on you by the scale, but if you also draw the free body diagram of the scale, yeah, let's do that. What will be the free body diagram of the scale, right? Free body diagram of the scale, it's touching the floor. So there's a normal force on the scale by the floor. And it's also touching your feet. Your feet is exerting a normal force on the scale by you. Okay, can you see any Newton's third law pairs between this, and this? Is there any Newton's third law pair? Yes, right? On scale by you, on you by scale. So these two are equal by third law. Now, if A is 0, then these two are equal by second law or first law. Okay. Same thing, right? First law just says I have to balance. So what the scale is measuring is the normal force on the scale by you. This is what the scale is measuring. By third law, it's equal to the force on, it's the normal force on you by the scale because you're just flipping it. and equals to mg. So yes, it's very, very indirectly measuring your weight. But as soon as the elevator now is accelerating downwards, right? As you can see, right, if you accelerate downwards, now you will have a reduced normal force. This is on you by scale, right? But that is the same, identical to the normal force on the scale by you. So that's by third law. So this is what you measure, and now it's reduced. Now, how fast must you accelerate until the normal force is zero? How fast, right? Everything is pointing downwards in my equation. So what must A be downwards for you to be, for the n to be zero? Well, if that's g, right? So that's when the elevator is accelerating downwards at the same acceleration as that as g, then you don't feel any normal force. So what do we learn? We learn that if the frame of reference is accelerating the same rate as you feel weightless. But I'll put that in quote because now you know better. Is yes, you feel weightless, but what really is happening is the normal force is zero. So that's happening with the astronaut because the spaceship is accelerating at the same rate. It's accelerating due to the centripetal acceleration. You are accelerating due to the centripetal acceleration, so they feel weightless. And yeah, same thing. If you are in the elevator and it goes up, this time if it goes up, you need to plug in a negative value because this equation was written down assuming going down is positive. So if the elevator goes up, now you make that negative. Then here you have negative on negative. You actually increase the normal force and you feel heavier. Okay. So yeah, now you understand if you want to lose weight, you this is basically the apparent weight. What the scale? So apparent weight. If you want a definition, that's what the scales measures. Okay, and that is basically the force. More rigorously, right? Is the force on the scale by you. Okay, so on the scale by you, that's the apparent weight. Okay, yeah. So if you want to lose weight, and you basically there is mg, and that is always weight. There's nothing much you can do unless you can change the g. You can go on the moon, so you have a different g. That's one way to lose weight. But what you really mean is you want to lose mass, right? So be careful with these words, and now you understand a better concept and why weightlessness is also a very bad word. But you understand whenever you measure someone's weight, you're measuring the normal force on that person. Very important concept. You never really feel the force of gravity. What you feel is the normal force. And if you take that away, right? If you fall on an elevator, you will not feel the force of gravity at all. You just feel weightless, right? That's what you mean is you don't feel any counteracting force, so you don't feel the normal force. Okay, hope that all makes sense. And yeah, this nicely wraps up the topic of forces, and which will shift us into the next part of the course, and we'll look at the new idea of energy.